Allow me to introduce you to one of my personal favorite exoplanets, a world that truly challenges our understanding of planetary systems. It's called WD0806-661b, but in 2022, it was officially given the beautiful name Aura. This is a colossal world, initially estimated to be somewhere between 7 and 9 times more massive than our own Jupiter. It orbits a star named Maru, but Maru is no ordinary sun. It's a white dwarf, the cold, compact ghost of a sun-like star that exhausted its fuel and shed its outer layers billions of years ago. Now, one of the most compelling things about Aura, and the central mystery of our story today, is its temperature. Despite circling a dead, dim star that shines with only 1.5% of our sun's brightness, Aura maintains a surface temperature between 52 and 77 degrees Celsius, or 125 to 170 Fahrenheit. While certainly hot, this is a range where liquid water could theoretically exist. You might be wondering just how close it has to orbit this stellar ember to receive such warmth. Well, if you guessed it orbits at a staggering 2,500 times the distance of Earth from the Sun, you would be absolutely correct. To put that into perspective, if we placed Aura in our own solar system, it would be far beyond the Kuiper Belt, drifting near the very edge of the inner Oort cloud. So, how does it stay so warm? The initial explanation was simple: internal heat. Aura is so massive that it's on the cusp of being a brown dwarf. While it doesn't ignite hydrogen fusion like a star, powerful internal processes like gravitational contraction and radioactive decay generate a tremendous amount of heat, keeping it comfortably warm despite being in the frozen depths of space. This was a neat and tidy explanation. However, observations from the James Webb Space Telescope, while confirming an atmosphere rich in water vapor, ammonia, and methane, also delivered a bombshell. A recent paper analyzing this new data claimed a detection of a significantly lower mass, somewhere between just 0.3 and 1 Jupiter masses, albeit with a high degree of uncertainty. If this is Aura's true mass, then something truly strange is going on. As I mentioned, a planet's internal heat is a function of its mass and its age. More mass means more heat, but older planets have had more time to cool down. We know its star, Maru, is roughly 2 billion years old. Since planets typically form alongside their stars, Aura should be the same age, but a low-mass, 2 billion-year-old planet should have cooled to be frigid by now. It shouldn't be anywhere near its current temperature. The paper that presented this conundrum lists several potential solutions. Let's explore them, from the least to the most interesting. 1. The new mass measurement is simply wrong. The researchers acknowledge certain assumptions in their calculations that could be flawed. If this is the case, Aura might indeed be a high-mass giant, and its heat is no longer a mystery. Problem solved. 2. The excess heat is generated by tidal forces. In this scenario, Aura might not be alone. It could be a binary planet with a companion of its own. The constant gravitational tug-of-war between the two bodies would stretch and squeeze their interiors, generating friction and heat, thus explaining the elevated temperature. 3. This is the most profound possibility. What if Aura is a single planet, the low mass is correct, and it is indeed this warm? The only way for all three of those things to be true is if the planet is much, much younger than its star. The models suggest it would have to be only 60 to 180 million years old. This would mean that Aura did not form with Maru. It was instead a rogue planet, a world born without a star, wandering the galaxy alone for millions of years until it was gravitationally captured by Maru. To complicate matters further, Aura's radius has been measured to be about 12% larger than Jupiter's. This fits perfectly with the first hypothesis of an old high-mass planet. However, it also fits perfectly with the third hypothesis, because young, still contracting planets are puffy and larger for their mass. So, could Aura be a captured interstellar wanderer? The idea might seem like science fiction, but it's statistically plausible. Some estimates suggest there are trillions of rogue planets in the Milky Way, vastly outnumbering the stars. Calculations predict that roughly 1 in every 1,000 stars may have successfully captured a rogue planet into a permanent, stable orbit. These captured worlds would typically find themselves in orbits that are extremely distant and eccentric, just like Aura's. If this hypothesis is true, it paints an incredible picture of Aura's environment. The light from its star, Maru, would be so faint from 2,500 astronomical units away that it would appear as just another bright star in an endless pitch-black night sky. The world would be illuminated by nothing but starlight.